Welcome to Spring LIB.
Hi there, so for this problem we are told that the yellow sodium D lines have wavelengths between 589 and 589.6 nanometers. Now, when they are used to illuminate a Michelson interferometer, it is noted that the interference fringes disappear and reappear periodically as the mirror M1 is moved. So the question is, why does this happen? Now, there are two interference patterns formed, one by each of the two wavelengths, okay? So there are two interference patterns. Okay, now the fringe patterns overlap but do not interfere with each other. Accordingly, when the bright fringes of one pattern occurs at the same locations as the dark fringes of the other patterns, there will be no fringes seen, since there will be no dark bands to distinguish one fringe from the adjacent fringes. To shift from one no fringes occurrence to the next, the mirror motion must produce an inner number of fringes shift for each wavelength, and the number of shifts for the shorter wavelength must be one more than the number for the longer wavelength. So with that, we see that the path length change is twice the distance that the mirror moves. One frame shift corresponds to a change in path length of lambda, so that corresponds to a mirror motion of half lambda, where lambda is just the wavelength. Now, let capital M be the number of frame shift produced by a mirror movement of delta x. So we will have that N1 is equal to 2 times delta x divided by the initial wavelength, the wavelength 1. And for N2, we just have the same, but in terms of the wavelength 2. And so we know that the condition for this, as I said before, N2 is equal to N1 plus 1. And then we just can substitute these definitions in this expression. So we will have 2 times delta x divided by the wavelength 2 is equal to 2 times delta x divided by the wavelength 1, and this plus 1. And then in here, solving for delta x, we will have that is equal to the wavelength 1 times the wavelength 2, and this divided by 2 times the difference between the wavelength 1 and the wavelength 2. So with that, we substitute the values that we are given for this, so that will be the product between the wavelengths, that is 589.6 nanometers and 589 nanometers, and this divided by 2 times the difference, so that will be 2 times 0.6 nanometers. So from this we obtain that delta x is approximately a value of 2.9 times 10 to the minus 4 meters. So that's a solution for this problem. Thank you.